Imagine two spacecraft traveling at thousands of kilometers per hour, needing to meet and connect with extreme precision in the vastness of space. This process is called docking. Docking is the controlled connection of spacecraft, allowing for craft transfer, fuel resupply, and module assembly in space. It has been critical in space exploration, from the Apollo-Soyuz Test Project's modern mission with the International Space Station. Without docking, long-term space mission and space station operation wouldn't be possible. There are two main types of docking: hard docking, which involves a secure mechanical lock, and soft docking, which often uses magnets or robotic assistance for smooth contact. Docking is now shifting towards autonomous and AI-driven systems, making future deep space mission more feasible. In this presentation, I will explain the different types of docking, the control system behind it, and real-world examples. Now that we understood what docking is, let's explore the different types of docking and how they work. Docking can be classified into two main categories: hard docking and soft docking. In hard docking, spacecraft use mechanical latching system to form a rigid connection. This is the method used by spacecraft like a Soyuz, Dragon, and the Apollo modules when docking with space station. Hard docking ensures a strong physical connection, but it is also requires precise alignment and controlled contact to prevent structural damage. On the other hand, soft docking is more feasible approach. Instead of mechanical lock, it relies magnets, dampers, or robotic assistance to make initial contact and stabilize the spacecraft before the final latching occurs. This technique reduces impact forces, making it particularly useful autonomous. The International Docking System standard used by modern space vehicles incorporates elements of both soft and hard docking for safety and efficiency. Another important distinction is between manned and unmanned docking. In manned docking, astronauts actively control the spacecraft, manually guiding it into the position using thrusters and docking sensors. However, with advanced in AI and autonomous, most modern missions like SpaceX Dragon capsule use autonomous docking system, where onboard sensors and computers calculate the exact approach trajectory and execute the docking procedures without human. As space exploration moves toward deep space mission and orbital construction, efficient docking methods will be essential. Future concepts like magnetic docking and AI-driven docking will further improve safety. Next, we will deeper into the different docking mechanisms and how they function in real-world applications. Now that we understand the type of docking, let's take a closer look at different type of docking mechanism used in space missions. This mechanism ensures a safe and secure connection between spacecraft, whether it's craft transfer, cargo delivery, or assembling space structures. One of the most widely used docking mechanisms is mechanical docking. This method relies on physical latches, coil rings, and locking mechanism to form a rigid connection between spacecraft. A great example is the Apollo docking mechanism, which enabled Apollo spacecraft dock with the lunar module. It used prop and drag system where the spacecraft had a prop that latching into the drag, creating a secure mechanical link. Today we use more advanced systems like International Docking System Standard, a universal docking standard used by modern spacecraft such as SpaceX Dragon, Boeing Starlink, and future lunar missions. International Docking System Standard allows different spacecraft to dock, ensuring global compatibility. Mechanical docking is reliable but requires high precision during the approach to prevent damage. That's why we new technology like magnetic docking are being explored. Instead of physical latching, magnetic docking relies on controlled magnetic forces to attract and align spacecraft. This method is particularly useful for CubeSats and small satellites where reducing impact forces is critical. In a typical magnetic docking system, electromagnets generate forces that gradually bring two spacecraft together. Once aligned, a locking mechanism can be engaged or magnets can unhold and connection. What is the advantage? The reduced risk mechanical failure and allow for multiple docking and undocking cycle without physical wear. Magnetic docking is especially promising for autonomous refueling station, modular space structures, and swarm of small satellites working together. The future of docking is moving toward robotics and AI-driven docking. Traditional docking relies on human control, but many modern spacecraft now use sensors, cameras, and mechanical learning algorithms to perform docking autonomously. For example, the Canadarm2 robotics arm on the International Space Station assists in redocking, and bartering spacecraft like a Japan HTV cargo model. This arm uses virtual and laser-guided sensors to capture approaching spacecraft and guide them into position. SpaceX Crew Dragon, on the other hand, uses full autonomous docking system. It calculates trajectory, velocity, and orientation in real time, making fine adjustments using onboard thrusters. The entire docking process happens without human intervention, a critical step toward deep space mission where astronauts may not always able to manually control the spacecraft. NASA and ESA are also testing AI-based docking system, where spacecraft learn from previous docking attempts to improve efficiency and safety. Future Mars missions, asteroid mining operations, and space station explorations will depend on these autonomous docking technologies. As we, as we push further this space, reliable and efficient docking mechanism will be the backbone of space exploration, orbital construction, and deep space travel. Whether it's mechanical latching, magnetic attraction, or fully autonomous AI-driven docking, this technology will be defined for future mission connect, refuel, and expand beyond Earth. In the next section, we will explore real-world docking examples and how these systems have been used in historical and modern space missions. Docking is not just about bringing two spacecraft together. It requires precise calculations, real-time adjustment, and intelligent control system to ensure smooth and secure connection. This is where guidance, navigation, and control system come into play. The guidance is the process planning, the optimal trajectory to reach the docking point. Navigation determines the spacecraft's current position, velocity, and orientation using onboard sensors. The control ensures that the spacecraft follows the planned trajectory by adjusting its thruster and orientation. In simple terms, GNC works like pilot for an autonomous docking vehicle, making continuous calculations to ensure precise and safety approach. For example, SpaceX Crew Dragon spacecraft uses an advanced GNC system that autonomously aligns itself with accurate docking requires a combination of sensors to measure distance, velocity, and orientation. Some of the key sensors. LiDAR uses laser pulses to measure distance with extreme precision. This is especially useful in autonomous docking, where real-time 3D mapping of the docking target is required. Cameras track visual markers to docking port, allowing AI-based vision system to analyze orientation and alignment. NASA LIDS use optical sensors to guide spacecraft during approach. Radio frequency sensors provide distance and velocity data useful tracking trajectory, even when direct visual contact is lost. This is how Soyuz spacecraft dock with the ISS, using radar-based core systems. Some docking systems, especially for CubeSat, use magnetic sensors to detect and align with another spacecraft magnetic field, enabling smooth and low-impact docking. Once the sensor gathers data, the spacecraft control system must decide how to adjust its position and velocity. Different control strategies are used depending on the mission's requirements. One of the most simplest and most widely used control methods is PID control, which continues to adjust thruster based on the position and velocity errors. PID works well for small correction but struggling with high dynamics control scenarios. A more advanced approach is model predictive control, which predicts future spacecraft movements and optimizes control inputs accordingly. Instead of reaction to errors after occurs, MP is anticipated the best thruster adjustment to minimize fuel consumption and docking time. Finally, sophisticated docking systems use trajectory optimization algorithms to plan the best paths in real time, taking into account fuel efficiency, time consumption, and unexpected disturbances. If an error occurs, adaptive control algorithms recalculate the approach strategy and ensure a safe docking. Without precise control system, docking would be dangerous and inefficient, whether using simple PID controls or advanced AI-driven NPC models. These control strategies ensure that spacecraft can dock autonomously, safely, and efficiently, a critical capability for the future space station, deep space missions, and safety services. Up next, we will look into the world docking examples and how these control techniques have been used in historical and modern missions. Now that we understand how docking works, let's look at some real-world examples where these technologies has been successfully used. From the first international docking to modern autonomous system, docking has been a critical role in the space exploration. One of the most historic docking events was the Apollo-Soyuz Test Project in 1975. This was the first international space docking mission, bringing together the United States and the Soviet Union during the Cold War. Apollo and Soyuz used complete different docking mechanisms, so engineers have to design a new system called Apollo docking mechanism, which works like an universal adapter. The spacecraft successfully docked the Earth's orbit and autonomously connected the joint experiments, making the first step toward the global space cooperation. This mission set the foundation for the future partnership, including the International Space Station. Today, docking is the routine but critical part of the space mission. The International Space Station relies on different spacecraft to dock and deliver cargo and crew. The Soyuz spacecraft used Russia follows the traditional docking process. Older Soyuz models were manually piloted by astronauts, but modern version used the Kurs radar system to enable autonomous docking. The system tracked ISS position velocity adjustment Soyuz thruster for smooth approach. On the other hand, SpaceX Crew Dragon introduced fully autonomous docking system. Using cameras, LiDAR, AI-based navigation, Dragon automatically aligned itself with the ISS docking port and complete the process without astronaut interventions. This is the game changer for future deep space mission where manual control wouldn't always be possible. While docking has traditionally been a large spacecraft, CubeSat small modules satellites are now exploring the docking technology for future space operations. One notable example is the MIT Paris project, a series of small robotic satellites tested inside of ISS. These free floating robots use autonomous navigation and docking algorithms, helping researchers understand how the future satellites can be assembled in space. Another project, ROSA, is an experiment on how spacecraft could dock with and attack two large satellites, forming model space structures. These concepts could lead to autonomous refueling stations on orbit, repairs, and self-assembling space habitats. From the Apollo-Soyuz handshake in space, fully autonomous docking with Crew Dragon docking technology has evolved dramatically. Future mission will be really on CubeSat docking, AI-driven system, and even magnetic docking create self-sustaining space structures. Next, we will explore the future docking, how AI, machine learning, and magnetic forces will shape the next generation of spacecraft docking systems. As we push deeper into space exploration, the future of docking is evolving rapidly. From fully autonomous spacecraft to magnetic docking and model space station, new technologies will redefine how the spacecraft connects its orbits. Today we will already see autonomous docking with SpaceX Crew Dragon, but future systems will be even more intelligent and efficient. NASA is developing AI-based docking systems that use machine learning algorithms to improve precision and reduce fuel consumption. For deep space mission where the communication delays make a real-time manual docking impossible, spacecraft will need to dock completely autonomous. Future Mars missions and asteroid mining operations and lunar operations will depend on these technologies. As research progresses, combination AI-driven control, magnetic docking, and precision navigation will open the new possibilities for small satellites and deep space missions alike. Throughout this video, we have explored the fundamentals of docking, the different types and mechanicals used, real-world examples, and future autonomous docking systems. Docking is the critical process for the space mission, enabling craft transfer, station assembly, and satellite servicing. Modern docking systems use mixed mechanical, magnetic, and robotic technologies to improve safety and efficiency. Autonomous docking and AI-driven control systems will play a critical role in the future deep space missions. Magnetic docking and CubeSat docking experiment could revolutionize how the small satellites interact with in orbits. The ability to dock safety and efficient is key to future space explorations. As we move toward a new era of space station, lunar bases, and deep space travel, docking technology will continue to evolve, making space more accessible than before. Thank you for watching. I hope you find this discussion insightful. If you are interested in the learning more, check out NASA, ESA, and SpaceX's latest research on autonomous docking. See you in the future space explorations.